Hello everyone, my name is Ernest Kirbagaran and I'm here to present our paper, Multigraph Approach Towards a Scalable, Robust Lookalike Audience Extension System. Here is the agenda for this talk. First, we will start with the background of the problem, then we'll have a look at the proposed method, followed by the results from the experiments, and finally, we'll conclude with the recap and direction of future work. Let's start with the background. So what is a lookalike model? It's a model in the ad tech world that identifies customers who look exactly like a target audience or a seed set. The primary goal here is to build a larger set of audience from relatively smaller segments to create reach for the advertisers. The target audience or seed audience is usually a set of customers who have responded positively to the ad campaign in the past. That is usually by clicking on the ad. The general approach to build a lookalike audience is to find users among the global set of users who share similar demographic and behavioral profiles with the seed set users. The hypothesis is that users with similar profiles tend to act alike. In other words, users similar to the seed set users are more likely to respond positively to the ad. The data available for advertisers today is highly complex, high in dimensionality, and extremely sparse. Building an effective lookalike model with this high dimensional sparse data is very challenging. Another challenge is low latency requirements of ad tech business. To overcome these two challenges, we use a multigraph approach to build an accurate lookalike model that is capable of low latency predictions. Now let's talk about the data available for lookalike modeling, our approach to this problem, and the scoring methodology which we employ to get accurate extensions. Speaking about data, there are generally two types of user data available for lookalike modeling, demographics and behavioral data. Demographic data is usually static, and some of the demographic features are high cardinal in nature. This data is also sparse. Among hundreds of demographic variables that an advertiser can collect, he gets only a few demographic information about every single user. Behavioral data, on the other hand, are data such as users purchase data, mobile application usage data, user interest and intent data. Unlike demographic data, behavioral data is dynamic and a user can have multiple values for a single behavioral feature. The cardinality of the behavioral data is usually very high. So we have a dual objective here, accuracy and latency. The extended set of users has to be as close as possible to the seed set in order to have a good lookalike output, and the retrieval of the extended users has to be fairly quick. We propose to build a deterministic k nearest neighbor multigraph where every user is connected to k most similar users. Here, separate graphs are built for demographic features and different behavioral features. The graphs are then combined to form a multigraph. Building a multigraph helps us to avoid certain types of features getting higher importance in the retrieval task. In other words, every feature is equally treated in a multigraph. The graph building process itself is a one-time offline task. And once the graph is built, the extension is fast as it involves only the retrieval of neighbors from the multigraph. So how do we build this deterministic KNN graphs? Building KNN graphs has quadratic complexity and is hence not computationally feasible with large datasets. So we use an iterative method known as NN descent to build the multigraph. In this method, we start with the random graph where each user is connected to k other random users. Now, we need to iteratively update the neighbors of every user. We do that by exploring the neighborhood space of the user. So once we run enough iterations, the NN descent algorithm is guaranteed to converge under two conditions. The number of neighbors for every user k has to be sufficiently large, and the distance measure used to compare two users should be a complete metric. Now, coming back to our data, we have demographic features that are mostly categorical and behavioral features that can take multiple values per user. So, we have to use different approaches and matrices to build graphs for these two types of features. Now, in order to build a graph for a demographic feature, we need to define an appropriate metric. To do that, we consider each feature in the demographic feature set as a dimension in the n-dimensional feature space. Now, to calculate the Euclidean distance between any two users in space, we need to find the relative distance between the two feature values in each feature dimension. We use Hellinger distance as a proxy for this relative distance. Once we have the Hellinger distance between the feature values, we can calculate the Euclidean distance between any two users and employ it as a distance metric in the NN descent algorithm. Moving on to behavioral graph, as you've seen earlier, behavioral data is highly cardinal and the distance measure break down in high dimensional spaces. Also, NN descent algorithm won't converge to the local minimum, won't converge to the global minimum if the feature dimension is large because of hubness. So to build a KNN graph for a behavioral feature, we need to reduce the dimensionality through some form of embedding. Let's take an example of the mobile app usage data. There are more than 250,000 active apps, and every user can have somewhere between 5 to 200 apps on their mobile. So in order to build a user graph, we first need to embed these apps. In other words, we need to get a embedding matrix for every app. So we do this by factorizing the global co-occurrence matrix. Now, after we do this factorization, every app is represented by a vector of length n, that n is the embedding dimension. If m is the maximum number of apps every user can have, where m is strictly less than n, where n is the embedding dimension, then each user can be represented as a m by n matrix. In other words, every user occupies an m-dimensional subspace given by the embedding vectors inside the n-dimensional embedding space. Now, in order to calculate the distance between two users, we need to calculate the distance between the two subspaces occupied by those users. For this, we use the modified caudal distance, which is again a complete metric. The behavioral graph is built using this modified caudal distance as a metric. After the multigraph is built, the next step is to retrieve the neighbors once we receive the seed set from an ongoing campaign. The retrieved neighbors are the candidate users for the extension. We need to score the candidate users based on the likelihood that they belong to the seed set. This depends on feature values of the candidate user and the structure of the multigraph. We use weighted information value to calculate the importance of the user features of a candidate user. In addition to the weighted information value, we also use two other matrices. One is the number of seed set users in the neighborhood of the candidate user and the number of edges between the candidate user and the seed set user. So every candidate user is scored, and the top candidate users based on the score are provided as output of the look-alike model. Coming on to the experiments, we ran two sets of experiments to test our model: online A/B tests on real-world ad campaigns and a seed set recovery task. In the first set of experiments, we ran different campaigns across different industries. The initial campaign runs were run on randomly selected users to get the seed set. Then the user extension was obtained using our multigraph model as well as using LSH model and similar X models. The table shows the click rates from the different models. Here the baseline is the click rate achieved during the initial run to get the seed set. Our model performed consistently better than the other two models. We also ran a seed set recovery experiment where we evaluated how well the models can recover the original seed set from the initial campaign when we extend only on a subset of the seed set. Again, our model performance was better than other models. For reproducibility, we ran the seed set experiment on the ad form click prediction dataset. Here again, the multigraph model gave better precision values than the other two models. Conclusion. We propose a multigraph lookalike audience extension system. Allowing different graphs for different categories makes neighborhood searches more robust and accurate. The model is computationally efficient during prediction time as it involves only retrieval and scoring of candidate users. The model can be easily scaled to millions of users. Real-world experiments show that our model achieves better click-through rates than existing lookalike architectures. Our model performs well in segment recovery tasks as well due to the deterministic nature of the graphs. In future studies, we would like to account for changes in short-lived user data, such as purchased intent information. Thank you.